Your threads aren't slow, they are waiting. The real enemy is a lock held just a little too long. Let's get started. Hey, welcome back. Fresh coffee, clear mind, you're now ready for the clean code C++ experience. Ever had an app freeze up exactly when you're trying to do something important? Or maybe you invested in a super fast computer, but your software still feels slow and sluggish. Well, guess what? Most of the time, the hardware isn't the culprit, it's how your software handles multiple tasks. Today I'm going to reveal a powerful secret to building blazing fast modern C++ apps. Concurrency. Specifically, I'll show you one golden rule that'll instantly boost your code's performance. So, what is a critical section? Let's imagine you have a shared resource, like a total sales counter for an online store. Multiple threads might be trying to update this container at the same time as new sales come in. If two threads try to add a scale amount simultaneously, you could end up with a wrong total. It's a classic race condition. To stop this from happening, we use a total called a mutex, which is short for mutual exclusion. Think of a mutex as a key to a private office. Only one thread can have the key and go into the office at a time. The code that's inside that office, the part where the thread has locked the mutex to safely work with a shared data, that's our critical section. While one thread is in that critical section, any other thread that needs to access the same counter has to wait outside. They're literally blocked. Now you can probably see the problem here. If the thread inside the office takes a long time, all the other threads are just stuck in a queue, waiting. This is called contention, and it's the enemy of high performance code. Basically turns your amazing multi-core processor into a single lane road during rush hour. Our job is to make that critical section as brief as we possibly can so the traffic of threads can keep flowing. Let's look at a very common mistake. This is a perfect example of what you shouldn't do. Here's a function that needs to do some complex calculation and then add the result to a global total. Okay, let's break this down together. First, we have got our necessary includes. Then we declare a global double called gTotalSales and a global mutex called gSalesMutex. Now look inside the calculate and add sales function. The first thing we do is create a lock guard. The second this line of code runs, our thread grabs the lock on the mutex. This is a good use of the RAII pattern, which stands for Resource Acquisition is Initialization. It guarantees that our lock is automatically released when the function ends. That's a great safety feature. But here's the problem. Look what happens right after we lock the mutex. The thread starts a heavy calculation, a for loop that runs a million times. This calculation is entirely local to the thread, doesn't touch the shared gTotalSales variable at all. Yet because we locked the mutex at the very top, any other thread that tries to run this function is completely blocked. It has to wait for the entire long calculation to finish before it can even start. We have turned the whole function into a critical section when in reality only one tiny piece of it needed protection. This is a classic case of holding a lock for way too long, and it'll kill the performance of your application. So how do we fix this? The solution is beautifully simple. We only lock the mutex for the exact moment we need it. Look at the difference here. It's a small change, but it's incredibly powerful. We first do all the heavy lifting, the big for loop calculation, completely out in the open. No lock is being held. Other threads can be doing this exact same calculation on other processor cores at the exact same time. There's no waiting. Then only when we have our result and are ready to update the shared total sales variable do we open a new scope with those curly braces. Inside that small block, we create our lock guard. The lock guard is acquired. We perform the one single addition that needs protection and then we hit the closing brace. The moment we exit that scope, the lock is immediately released. The critical section is now just a single line of code. It's tiny. We have minimized the time our thread holds the lock, which means other threads spend less time waiting. This leads to much better performance and allows your program to scale beautifully as you add more threads. Plus, the code is even clearer now. That tight little scope visually signals to anyone reading the code exactly which part is sensitive and needs to be protected. Hope you found that helpful. This is just the beginning though. Jump into the masterclass at alcoacademy.com to dive deeper and keep exploring my channel for more videos. Remember to hit that like and leave a comment. I appreciate every single one.